Hey guys, welcome back. In the last couple of videos, we have understood what is timing path and what is timing arc and other concepts. So now in this video, we will deep dive into timing path and understand how to read a timing path and understand its parameters and go through a timing path to debug any problem with the timing path or any constraint related to it. So let's get started.
So guys, this video was a little longer than usual, about more than 20 minutes. But I want you to keep your focus until the end of this video because the concepts in this video are very important and they lay the foundation for a static timing analysis. In order to go further and understand further videos, this video is very important and it cannot be split into multiple videos because the concepts are consistent and they are continuous. Okay, I hope you understand and keep your focus until the end of this video.
So as we have seen in the previous videos, there can be multiple different types of timing paths. Okay, so there it is mainly classified into two types. One is internal paths and other one is IO paths. So internal paths consist of paths like register to register. This includes latches and the register to memory or memory to register. These classifications of register to memory or register to ICG and ICG to register, these are done specifically for the optimization purpose and also for the analysis purpose. Okay, these are called internal paths because these start points and end points will be within the block itself. Okay, now next is IO paths, also called as interface paths. These interface paths are basically starting from some other block or the port to the block. So what happens is for the block, it is coming from the input port or going to the output port. Okay, so the register to output port or input to the register, these are the two different paths. And there is also possibility where your signal can go through your block completely. Both start point and end points will be ports where your input port will be your start point and the output port will be your end point. It will be also called as feed through paths. Okay, also user defined path groups can be there. That is not our focus here. So let's go over a timing report. For the sake of simplicity, I have used a register to register path. In this case, it's a very simple path. For us to understand each and every terminology, this will be very easy for us. So what you are looking at now is actually a timing report. So it contains three main parts. This part of the report is called header, where it gives the main information about the path, and then it gives the description of the path and what are the contents of the path, what are the cells in the path and their delay and other details. And the end, what you get is a calculation of the slack, how the slack is calculated. Okay, so this is the main three parts of your timing report. So let's start with the header part. All right, so in the header part you have a start point and the end point. All right, so there has to be a start point and end point for every timing path. All right, so also there should be something, there is something in the bracket as you can see. So this is very important details. Okay, so a start point in case of registers is always a clock pin, and in case of endpoints, it is for a register, it will be a data pin. All right, this is in the functional mode. A start point has to be a clock pin for the registers. Now this is giving some information to us saying that the start point is actually an positive edge triggered flip-flop or rising edge triggered flip-flop, which is clocked by CLK core. This is the clock which is actually clocking this start point. Similarly, the endpoint is also clocked by CLK core, but in this case it is the same clock which is clocking them, but there could be some cases where the clock can be a different one, right? This can be CLK core and this can be something else. In that case, it is called a cross clock domain path, also called as CDC path. So those are little complicated ones. We will look those paths later in the upcoming videos, but this is a simple path which most likely you will encounter. All right, so also one thing that can be missing is some cases it may not give you this information that this clock information is not present. In that case, that is a serious problem of constraint. Okay, that constraint is missing over there. What this last common pin is signifying is that the clock CLK core is going to the start point and the end point, both of them. But if you trace back both of these paths where the clock is driven to this start point and end point, you will not find any common point until the CLK core is what this last common pin is signifying. Okay, there is no common path to the clock between this and this other than the CLK core, which is the source of the clock itself. So this is what the path we are referring to, which is register 10 and register 11. Okay, the data path is basically or a clock pin of a launch flop to the data pin of the capture flop. This path is basically called data path. So this is the launch clock path and this is the capture clock path. In this case, I haven't shown any common path between them. Okay, but there could be in some other cases it is possible that you will have common paths. Like for example, you can take this one where we have some common path between the launch and capture clock paths. All right, so this entire thing is the launch clock path and this entire thing is the capture clock path, right? So this is the point where you can see there is an inverter here. This is common to both launch and capture clock paths. So the output pin of this inverter, which is the EE inverter 2 output, will be the last common pin to both register A and register B's clock path. This is very useful in analyzing a lot of things like CRPR and other things. So that's why this information is mentioned in the report. By default, the tool PrimeTime creates the path group for each and every clock. So in this case, it has created a path group called CLK core. So that's why it is telling this path group is actually CLK core, but it could be any other path group which you are creating with also, right? If we create a path group name differently for this path, so it will be that name which is coming. All right, so next is the path type. What type of path it is, what are we looking at? So this is very important. Are we looking at the setup violations or are we looking at the hold violations? Max indicates actually we are looking at the setup violation, right? So if it is min, then it will be actually referring to the hold path, right? This is a setup path. So wherever it is written as recalculated, it is actually referring to PBA analysis. Okay, there are two types of analysis that the tool will be able to do. One is PBA analysis and other one is GBA analysis. So graph based analysis is pessimistic, but the PBA, which is path based analysis, is more time consuming, but it is very accurate in nature. If it is GBA, then it wouldn't have given this recalculated as mentioned here. All right, so next comes the sigma. So sigma is mentioned here, which means this path is basically generated based on the OCV variations. All right, so OCV especially in this path is reported based on the latest POCV, a parametric on-chip variation, where the main delay will be calculated by mean plus n times the sigma. All right, so you can see that the delay is basically mean plus n times sigma is what I'm saying. So when I say n times sigma, this both mean and the sigma values actually come from the library of any cell. All right, but what is this n? Where is this n, which is a multiplier, coming from? That is what the report is telling as 3. All right, the sigma value which it is showing, which is 3, is actually the n value here. For example, what I'm saying is basically if you can take any of these delays over here, which is path, it is saying, so this is the mean and this is there is something called as sensit, which is sensitivity, and this is actually the actual sigma value. The standard deviation, which is 5p, is here. So the actual value of incremental delay, which is 219 ps, this is actually created by 202 plus 3 times the sigma value. Okay, so that's how we have got 219 ps. So that's the value that it is referring to. This is the sigma value of the for the LVF values that we get for the library. This is a sigma multiplier or a standard deviation multiplier. So then comes this part where it is giving information about the path. What are the cells in the path, and what is the delay at each and every timing point. All right, so there are some columns that I have listed here, but it can be multiple other columns that can be reported. For example, we can report fan outs, we can report d rates and multiple other things. But if you report, just do report timing, this is usually what you get. You will get just a simple a report where only few columns will be present, very important columns will be present. All right, so this is one very important parameter called timing point. Okay, this timing point refers to each and every pin where timing is defined, the value of the delay is defined. All right, and then the capacitance at each and every point where you find, and also the transition of the signal at each and every point is defined, timing point, and the mean value of the delay is defined at each and every point. And then the incremental delay here refers to the delay at each and every cell. All right, separately it is given. Like for example, this is 116 ps given by this cell itself. The delay of this cell is basically 116 ps, and delay of this cell is 27 ps. But this path delay is basically the accumulated delay of all these things. So you will be adding basically 219 plus 116, which becomes 336. All right, so this is another information that is present. And also you might be seeing that there is something called R and F which is present over here. So this basically says that the signal is coming, and where it is actually rising and where it is actually falling, it's that detail is being given here. So you might be seeing that this R and F is only over in certain portions, but after before this flop, that R is not present, and um, after this arrival time there is no R present, right? So okay, only over here it is present. So this is because that only this much part of the report is basically your data path. All right, you can see that the register 10 5 pin to the D2 pin of the register 11, this is actually our data path. But other pins which it is telling that this clock network delay and this other part, this is actually not the data path, this is actually clock path. So in this case, as I mentioned, this is a simple report timing command where we haven't mentioned any other switches. Okay, there can be a switch called path type full clock. In that case, if we provide path type full clock or full clock expanded, in that case we will get the cells within this clock path as well. Now you see that there is something called as clock network delay. So this clock network delay is basically the delay or the insertion delay of the clock network path or launch clock path. All right, so it took from the port or the source or the definition point of the clock till the 5 pin of this register, it took 219 ps to reach. So this is launch clock latency. All right, also called as insertion delay for the start point. And we also have end clock latency, endpoint clock latency, which is over here. So after this data arrival time, we will have the clock source itself. So after that you have the clock network delay again given here. This is basically 181 ps. If you want to find the skew, it is basically the difference between 181 minus the 219. That comes to around negative 20 ps or something. Sorry, negative 30 ps or something, 30 40 ps, right? So that's the difference. So you always calculate the skew as capture clock latency minus the launch clock latency, right? So that is your skew. You have to calculate by yourself in this case. All right, it's not giving anything specific, like this is the skew here. So and then some other parameters are also given here, something called clock reconvergence pessimism removal. We have understood what this parameter is in our previous video. So this is basically common path pessimism. In this case, you see that I have already told you that the last common pin is basically the definition, clock definition point itself, or the port. Because of that, there is no common path, right? So that's why there is no pessimism that's being removed. All right. So also there is something called clock uncertainty. This uncertainty is defined for some additional things which we don't have any control, right? For example, clock jitter, or in some cases we don't know how the waveform of the clock will be for certain advanced nodes. So that's why we add additional pessimism to our clock, so that we will not end up in any problematic situations, right? Then it is also showing the endpoint pin, which is register 5. So this basically, starting from this clock uh, definition point to the clock pin of the endpoint register, this entire path is basically the capture clock path. All right. So also you might have seen that there are two more important details here. One is the rise edge, where it is telling, here also it is telling clock, and it is telling rise edge, and one more here also it is telling rise edge. All right. So this is very important, because this is telling that the clock is actually rising here. All right. And also here it is telling clock is rising here, which means it has got one full cycle for this path. But in case, let's say, if this path was like clock was rising here and clock was falling here, in that case it would have got only half cycle in this case. Okay. So because of that reason, if you can see that the in the start point is basically 0 ps, and the end point is basically the 800 ps, which is actually our period over here, which is one full cycle over here. Okay. So this is one important detail. And also there is something called as propagated when it comes to clock network delay. Here also it has mentioned clock network delay propagated. What's the meaning of propagated? So in this case, the clock is being propagated from the definition point to your 5 pin, and from that the delay is being obtained. So this is actually the accurate delay from the clock tree itself. If it is not present, if let's say the clock tree is not built, in case of, let's say, place opt kind of timing reports, in that case we will not have this propagated. Instead, the latency will be provided to the tool by the command called set clock latency. All right. So other things is like you have the cell names present. This is actually the library name of the cell. It can be different with respect to different libraries. You will need to get those information from your vendors or the foundry, what is the meaning of these cells. All right, cell names. You one common thing is usually the X thing, X4 which is mentioned here, or an X8 mentioned here. Basically that's the drive strength of the cell. So that is one common thing. And here you can see that this is a buffer, this is a buffer, and it's saying D flip-flop, and many others. So finally you have got something called data arrival time. Data arrival time, where is the data arriving? Data arriving to D2 pin of the register 11, which is our endpoint, right? So the data is arriving 828 ps, and then actually when it was supposed to be arrived, right, that is called as it is required time, right? So data required time is basically calculated from this value, which is like, okay, we have 800 ps as our clock period, right? This is what the clock period is, but the network delay was 181 ps. So that 181 ps will be added, because this latency will be good for setup, right? That's why it will be added. 981 it becomes. And there is no clock reconvergence pessimism, so it's not removed. Clock uncertainty, we have removed 86 ps. Okay, so from that it becomes 895 ps is what the data required time is. But again, there is a library setup time of the endpoint itself, which is of this register 11. So register 11 has something like somewhere around 39 ps as its setup time, so that also will be subtracted. So it becomes 855 ps now. Before 855 ps the data has to be arriving. So when is the data is actually arriving? We saw that it is 828 ps. So you can see that the calculation is done something like this. We have 855 ps and 828 ps. But one thing that you can observe is somehow if we do 855 ps minus 828 ps, you will not get this value, right? It's not going to be 42 ps. So remember one thing, this is very important for you to understand, that this value is never calculated from this. Okay, the final slack is never calculated from the final values of these two values. Okay, it's always calculated from the mean and sigma. So in case of LVF or in case of POCV, the values will be calculated based on the POCV analysis, or in case of cadence it's called SOCV. So in this case it's basically subtracted from this value, okay, 876 ps, which is a mean value. You can see this is a mean value. So this mean value will be subtracted from this one, which is 88 ps it becomes, and then this 88 ps, and this is basically sigma, which is standard deviation. Now this has to be subtracted because we are considering the, it becomes 88 ps minus 3 times the 15 ps, which is basically 45 something ps it becomes. So what you will get basically is a 42 ps. So what is this statistical adjustment that value is given? So this value is just given so that we understand that because of POCV there is a variation from this required time and arrival time to this value. Okay, so if it's just saying that if you just subtract these two you will not get this value. If you just subtract these two you have to add this value to get this value. So this value is basically coming as a statistical adjustment from POCV, that is basically calculated like this. So this value of statistical adjustment is just signifying that the because of POCV your simple arithmetic subtraction between the data required time and arrival time will not work. That's what it is telling. So finally we get the slack, which is 42 ps here, which is positive, so we are safe. But in case if it is negative, then we have to understand and debug this path for any problematic things. In this case everything looks good for this path. Okay, there is also one thing that I missed out, which is this ampersand. All right, what is this ampersand which we are looking at? So this basically signifies that this delay is calculated based on the RC delay back annotated from a SPEF or a GPD file. Okay, that's what it signifies. So I hope you got a good understanding of how to read a timing report. Especially this is a setup report. There can be whole reports as well, and also there can be different types of paths. For this case it is reg to reg. We can go over multiple different paths in upcoming videos for different purposes when we are opening. All right, so this is the basic information about how to read and understand a timing report. All right, so thanks a lot for watching. If you have any questions, please put in the comment box. I can try to help you out with your doubts. All right, so if you like the video, please go ahead and subscribe to my channel, and if you want to contribute you can contribute through the super thanks as well. Yeah, thanks a lot.